Hi guys! So, in this section and in the next two sections, we're going to be actually performing the step-by-step hypothesis tests. Now first, we're going to focus on hypothesis tests for a population proportion. Alright, so for hypothesis tests, for any parameter, it doesn't matter it is for a proportion, mean, or standard deviation, or even variance, there are two methods to do hypothesis tests: the classical or traditional approach and the p-value approach. I will show you both methods in each section, okay? Now here's an example. Suppose a politician wants to know if a majority, more than 50%, of her constituents are in favor of a certain policy. The politician hires a polling firm to obtain a random sample of 1,000 registered voters in her district and finds that 534 are in favor of the policy. Do these results suggest that among all registered voters, more than 50% favor the policy? Or is it possible that the true proportion of registered voters who favor the policy is 50%, and we just happened to survey a majority in favor of the policy? So before we talk about how to carry out a hypothesis test, let's understand what we're really doing here, okay? Now this politician, she's wondering if more than 50% of her constituents favor the policy. And in our sample, we found that 534 favor the policy, right? Which means that 53.4% of the sample favor the policy because we have 1,000 people in our sample, right? Okay, so 534 divided by 1,000, that's 0.534, which is 53.4%, right? So this is our sample proportion. So you might say to yourself, why are we not just saying, well, it was 53.4%, so we're ready to sort of make a conclusion that more than 50% of people are in favor of the policy, right? Well, the idea is that this is only a sample of 1,000 people. So maybe there are just some people that happen to favor the policy, and getting 53.4% is not so surprising, and it is not really hard to get just by pure luck. So the whole point of this hypothesis test is to basically analyze how different this 53.4% is from 50% based on the size of our sample and the amount of variation we expect. If this is really different, right? If this 53.4% is really different from 50%, then we're gonna say, okay, we have enough evidence to say that more than 50% of people favor the policy, right? And if this turns out to really not be that different from this, right, then we might end up saying we cannot conclude that more than 50% of people favor the policy. So that is the whole point of running this hypothesis test. Okay, so these are our hypotheses. H0 is the proportion is 50%, so P equals 0.5 or 0.50. And what we're trying to get evidence for is that the proportion is more than 50%, right? So more than 50% of her constituents are in favor of a certain policy. So that's what we're trying to find evidence for. Okay, and from our data, we got the sample proportion is 53.4%. So that's P hat. Now, as I mentioned before, we are trying to analyze how different 53.4% is from 50%. If 53.4% is really different from 50%, that means 53.4% is considered unusual, which means that it is very unlikely to get a result like that purely by luck. And we're going to conclude that it is more likely that the true proportion of people who are in favor of the policy is more than 50%. Okay, so how different is 53.4% from 50%? To answer the question, we first look at the sampling distribution of p hat. Because if the sampling distribution of p hat is approximately normal, then we can figure out what values are considered unusual. Okay, so let's check the assumptions. All right, so first, SRS. The sample is a simple random sample. Okay, so it says that a random sample right here, so that is good enough. Check. Okay, number 2. The sample size is less than or equal to 5% of the entire population. So the sample size is 1,000. Is it less than or equal to 5% of the entire population of all registered voters in her district? I'm assuming so. In order for this inequality to be true, right, the size of the population it needs to be more than or equal to 20,000. Why? Because the 5% of 20,000 is 1,000, right? So if the population is more than 20,000 people, then this inequality is true. I am guessing that she has more than 20,000 registered voters in her district. So I'm just going to say yes to that. Okay. All right. Number 3. N times P times 1 minus P is greater than or equal to 10. Okay. So the sample size, 1,000, P, that is going to be the value of a null hypothesis. Why? Because we're always assuming that the null hypothesis is true until proven otherwise. So throughout the entire hypothesis testing process, we're always operating under the assumption that H0, the null hypothesis, is true. Okay, so P is 0.5. Okay, and then you multiply that by 1 minus 0.5. And that is 250, which is more than 10. Okay, so all assumptions hold. Perfect. So the sampling distribution of p hat is approximately normal. With the mean mu sub p hat, which is the same as p, so that's 0.5. Okay, and the standard error sigma sub p hat, which is the square root of p times 1 minus p over n, which is the square root of 0.5 times 1 minus 0.5 divided by 1,000. All right, so what we want to know now is how far 0.534, which is this number up here, 53.4%, how far this number is from 0.5. In other words, we want to know how many standard deviations 0.534 is from 0.5. And in order to figure out how many standard deviations there are between 0.5 and 0.534, we need to standardize this value. Okay, so let's do that. So first, okay, so we're going to take this value, 0.534, and we're going to subtract 0.5. So basically, you're finding the difference, right, between 0.534 and 0.5. And we're dividing the difference by the standard error. So that you can find the z-score. Okay, so if you punch these numbers in your calculator, you will get something like 2.15. Okay, so this means that in a standard normal distribution, (2.15) is somewhere here. And this number represents how many standard deviations 0.534 is from 0.5. So 0.534 is 2.15 standard deviations from 0.5. And this value, 2.15, is called test statistic. It's a standardized value that is calculated from sample data with the assumption that H0 is true. Okay, so let's read the classical approach, right? If the sample statistic is too many standard deviations from the population parameter stated in the null hypothesis, we reject the null hypothesis. Okay, so what they're saying is that if there are way too many standard deviations between these two numbers, then we're going to reject the null hypothesis because this number is considered way too far away from 0.5. That means that this number 0.534 is considered unusual, right? So we're going to reject the null hypothesis. So we do know how many standard deviations there are between 0.5 and 0.534. That's 2.15. The question is 2.15 too many standard deviations? Now, we learned before that more than 2 standard deviations are considered unusual, right? But in hypothesis testing, we have a more specific benchmark, which is determined by the critical value. Do you guys remember critical value from the previous chapter? Of course you do, right? So the critical value is the number on the borderline separating sample statistics that are unusual or significant from those that are not significant. So we use the level of significance, alpha. You guys remember alpha? Okay, to compute the critical value. So again, alpha is the probability of making a type 1 error, all right? So let's use alpha equals 0.05, all right? 5% error. Okay, so z sub alpha, which is z sub 0.05, and we're using inverse norm, right? And for the area, we need to use the left area to the critical value. So it's going to be 0.95, which is 1 minus 0.05, right? And mu is 0 and standard deviation is 1. Okay, so this is going to be 1.645. Okay, so this is the critical value, right? So 1.645, that will be somewhere here. 1.645. And what that means is that anything, right? Anything larger than 1.645 standard deviations from the mean is considered significant or significantly high. Okay, so let's go back to our question. Is 2.15 considered too big? The answer is yes, it is, because 2.15 is bigger than 1.645. So it is considered statistically significant. So this means that 53.4%, our sample statistic, this is considered too far above the population proportion of 0.5. So what is our decision? We're going to reject the null hypothesis in favor of our H1 claim. So what we're saying is that if the null hypothesis is true, right, the null hypothesis of P equals 0.50, if this is true, it is so unusual to get a sample proportion such as 53.4% purely by chance. You're not supposed to be getting something like this if the null hypothesis is true. But the fact that we did get 53.4% tells us that the null hypothesis of P equals 0.5 was likely to be a false assumption to begin with. So that's why we reject the null hypothesis and support the claim that more than 50% favor the policy. Okay, so here's the definition we just used. when observed results are unlikely under the assumption that the null hypothesis is true, we say that the result is statistically significant and we reject the null hypothesis. Okay, so the method we just used is called the classical approach. Okay, now another method of hypothesis testing is called the p-value approach. In this approach, we're going to determine how likely it is to get a sample proportion of 0.534 or higher. And we're going to do that by actually calculating the probability, okay? Probability of getting a sample proportion of 0.534 or even higher, right? So that probability is called a p-value. Okay, so here's a definition of a p-value. It is the probability of observing a sample statistic as extreme or more extreme than one observed under the assumption that the statement in the null hypothesis is true. So if the probability is small, then it means that it is unlikely to get a value such as 0.534, which means that the sample proportion of 0.534 is statistically significant, and we can reject the null hypothesis. Okay, so let me graph the sampling distribution of the sample proportion. Okay, and we have 0.534, okay, and what we want to find is the probability, so that's the area, right, under the curve, probability of getting 0.534 or higher. So we're looking at the area to the right of 0.534. Now on a z-scale, right, we know that it's 2.15 standard deviations from the mean. Okay, so the p-value, which is this area right here, is the probability of getting a sample proportion of 0.534 or higher, which is equivalent of the probability of z is greater than or equal to 2.15. Okay, so we're going to be using normal CDF function. So the lower, upper, mu, and sigma. So the lower will be 2.15, and the upper will be 1e99, and mu is 0, that's the mean, and the standard deviation is 1. Okay, so this is about 0.0158, so it's about 1.58%. Okay, so what this means is that, let's say you go out there and you get a sample, okay, and you calculate its sample proportion, p hat, right? The probability that you're gonna get the sample proportion, which is 0.534 or even higher, is only 1.58%. So this is the probability of getting a sample proportion which is 0.534 or higher. So this is called a p-value, right? Now the p-value approach says if the p-value is small under the assumption that the statement in the null hypothesis is true, reject the null hypothesis. Now what is considered small, right? So what we're going to do now is we're going to compare the p-value with the level of significance, which is alpha. Okay, so if the p-value is less than the level of significance, then we consider that p-value too small, and we're going to reject the null hypothesis. Okay, so our p-value, once again, is 0.0158. And our alpha is 0.05. This is from the previous page, okay? We used 0.05 for alpha. Okay, so clearly the p-value is less than 0.05. By the way, if you want to see alpha visually, then 0.05 is somewhere here. So this green area, so this is alpha, which is 0.05. And the critical value that corresponds to that alpha is 1.645. Again, this is from the previous page. Okay, so notice that this green area, which is alpha, is much bigger than the blue area, which is the p-value. Now, since the p-value is so small, smaller than the significance level, that it is so unlikely that we get a sample statistic such as 0.534 or even higher, purely by luck. So that implies that it is likely that the null hypothesis was not true to begin with. And we're more inclined to support the claim that more than 50% favor the policy. Okay, so our conclusion is that we reject the null hypothesis, okay, in favor of H1. Now, whether the p-value approach is used or the classical approach was used, the conclusions are going to be the same. So if you reject H0 using the p-value approach, you're going to be rejecting H0 using the classical approach. And if you fail to reject H0 using the p-value approach, once again, you fail to reject H0 using the classical approach. Okay, the answers should match. Okay, so at this point, we've introduced a pretty complicated new topic, this idea of hypothesis testing. So in the next page, I'm going to give you more concrete structure of steps to perform hypothesis tests. Okay, let's go to the next page. Okay, so here are the steps to perform hypothesis test for a population proportion P. Okay, step 1, state the null and alternative hypotheses. The hypotheses can be structured in one of three ways. Okay, we talked about that in the previous video, right? So you're gonna have either two-tailed or left-tailed or right-tailed test. It depends on the problem, right? So for two-tailed test, H1 is not equal to sign, and for the left-tailed test, H1 is less than sign, and the right-tailed test is greater than sign. All right, now P naught, okay, this guy right here, P naught is the assumed value of the population proportion. Okay, usually this value is given to you in the problem, so you're gonna have to look for it. All right, step 2, check the assumptions. Okay, so you're gonna have to check three things, right? SRS, and also the sampled observations must be independent, so n is less than or equal to 5% of the entire population. Okay, and number 3, n times p naught times 1 minus p naught is greater than or equal to 10. Okay, so make sure you check all these three assumptions. We want to make sure that the sampling distribution of the sample proportion is normal, right? Okay, step 3, state the level of significance alpha. All right, so alpha is given to you in the problem usually, so you're gonna have to look for it. But if it is not given to you for some reason, then use alpha equals 0.05, 5%. That is the default alpha value, okay? But usually it is given to you, so go ahead and look for that. Step 4, compute the test statistic. We talked about test statistic in the first page. So the formula is Z naught equals P hat minus P naught divided by the square root of P naught times 1 minus P naught divided by N. Okay, so we're going to be using this formula to determine how many standard deviations there are between the value in the null hypothesis and the sample statistic, right? Now, for step 5, you have two options, either the classical approach or the p-value approach. Okay, so for the classical approach, first you sketch the distribution. Okay, so for this one, you're going to be sketching the z distribution. Okay, and then you're going to show the critical value or values, and you're going to locate the test statistic. All right, now in order to find the critical value, you're going to use inv-norm function. Now for the two-tailed test, you have two critical values, one on the left and one on the right. So before you use inv-norm function, you're going to have to divide alpha, the significance level, by 2. And then you're going to use inv-norm to figure out the critical value. Now for the left-tailed test, you're going to have only one critical value on the left of the distribution. And for the right-tailed test, you're going to have a critical value on the right of the distribution. There's only one critical value on the right. Okay, let's do a quick example. Let's say alpha is 0.01, 1%. Okay, so if you're looking for the critical values for two-tailed test, then first you divide alpha by 2, which will give us 0.005. Okay, and then you do inv-norm. And then for the area, you're going to have to type the left area of the critical value you're looking for. So it's going to be 0.995, okay? And then 0, 1. So the mu is 0, and then sigma is 1. Okay, so pause the video, go ahead and try that on your calculator, and come back when you're done. Okay, so you should get something like 2.576. Okay, so that is the upper critical value, 2.576. This value on the number line right here. Now the z distribution is symmetric, so the left critical value is going to be negative 2.576. Okay, you just have to change the signs. Okay, so that's it for the two-tailed test. Now let's look at the right-tailed test next. Okay, so we're going to be using, again, alpha equals 0.01. Now for right-tailed test, we have only one critical value on the right side of the distribution. So the area to the right of the critical value is 0.01. So you are basically looking for z sub 0.01, which is inv-norm 0.99. Okay, once again, 1 minus 0.01, which is 0.99, and mu is 0, sigma is 1. And for this one, you will get 2.326. Okay, so the critical value is 2.326 for this one. Okay, now it's important that you do not divide alpha by 2 when you have a right-tailed test, because we're focusing only on one side of the distribution. We're using only one tail, which is the right tail, right? So we're not dividing alpha, the area, into two tails. Okay? All right, now for the left-tailed test, we can use the critical value of the right-tailed test, which is 2.326, and then you just need to change the signs, okay? So negative z sub alpha right here, that's basically negative 2.326, okay? This is basically negative z sub 0.01. You just have to change the signs, that's all. Okay, step 6. Now you're going to compare the critical value with the test statistic, and you're going to write the conclusion. In other words, you're going to decide whether the test statistic is in the critical region. Okay, so the critical region, when you go back to step 5, right? These tail area, these blue regions in the tails, right? These are called critical region. So if your test statistic falls in the critical region, then you're rejecting the null hypothesis. Because what that means is that your sample statistic, p hat, is way too far away from the assumed proportion P. It is so unusual to get something like that purely by chance. So it is unlikely that the null hypothesis is true. That's why we are rejecting the null hypothesis. Okay, now the p-value approach. First, you're going to sketch the distribution and you're going to show the p-value for the test statistic. Now, since the p-value is the area under the normal curve for this one, you're going to be using normal CDF to find the area. Okay, so for two-tailed test, the p-value is the sum of the area in the tails, right? Now, the area in the right tail is the same as the area in the left tail. So all you need to do is to find the area in one of these tails and then multiply the answer by 2, okay? So if you want to find the area to the right here, let's say normal CDF, and then Z sub 0, which is the test statistic, right? Okay, so that's the lower bound, right? And then 1E99, and then 0, 1. And that will give you the area to the right here. And then you're going to multiply the answer by 2, and that will give you the total area. So this area right here is that. All right, so for the left-tailed test, okay, then you're going to be calculating the area to the left of the test statistic. Okay, so you're going to be doing normal CDF, and so it's going to be the left area, so negative 1E99, and then Z sub 0, which is test statistic, and 0, 1. That's going to give you the left area. All right, and then for the right tail test, it's going to be the area to the right of the critical value. So normal CDF, test statistic, 1E99, 0, 1. Now, for the two-tailed test, the test statistic sometimes is a negative number. So if that happens, then you can still use normal CDF, but it's going to be negative 1E99 is the lower bound, and then the upper bound is going to be the test statistic, and then 0, 1, and then times 2. Okay? Now, step 6, you're going to compare the p-value with alpha, and you're going to write the conclusion. So if p-value is less than alpha, then you reject the null hypothesis. Otherwise, you're going to fail to reject the null hypothesis. Again, a p-value is the probability of getting the value of your sample statistic, or even more extreme than your sample statistic. Okay, so if the p-value is really, really small, that means it is so unlikely that you get a result such as your sample statistic, purely by chance. So we are more inclined to believe that our original assumption, our null hypothesis, was not true to begin with. Okay, so the final step, step 7, you're going to state your conclusion in the context of this particular situation. Okay, so remember, there are 2 types of conclusions. If H0 is rejected, then we're going to say that there is sufficient evidence at the alpha equals, so you're going to write the significance level here, level of significance to support that, and then you explain H1. Okay? Now it's very important, once again, if H0 is rejected, we always have sufficient evidence for H1. And the second type of conclusion, if H0 is not rejected, meaning if we fail to reject H0, then we're going to say that there is not sufficient evidence at the alpha equals let's say 0.05 level of significance to support that, and then you explain H1, right? So again, If H0 is not rejected, then we do not have sufficient evidence for H1. Okay, so these are the 7 steps for testing a hypothesis for a population proportion. In the next video, we're going to be looking at some real-life examples, and we're going to perform some hypothesis tests using these 7 steps. Okay, see you in the next video. Bye guys.